Something is glowing in the dark between the stars, and it should not be possible. Right now, as you listen to this, an object older than our Sun is racing through our solar system at 130,000 miles per hour, wrapped in an X-ray halo that extends for 400,000 kilometers, carrying chemicals that form the building blocks of life in concentrations 4 times higher than any comet we have ever measured, and in 8 days it will reach its closest point to Earth. The Japanese Space Agency just released the first X-ray image ever captured of an interstellar visitor, and what they found has sent shockwaves through the astronomical community. This object has 2 tails when most comets have 1. It is erupting in ice volcanoes. It glows green despite lacking the molecules that cause green fluorescence. And a Harvard astrophysicist is warning that its trajectory toward Jupiter is so mathematically precise that the odds of it being coincidental are 1 in 26,000. Tonight we're going to examine every piece of new data that has emerged in the last 72 hours, because what 3i Atlas is revealing about the chemistry of alien star systems, about the ingredients for life scattered across the galaxy, and about the possibility that we are not alone, will fundamentally change how you see our place in the universe. Stay with me until the very end, because the final chapter contains information that has not been widely reported, and it concerns what happens after December 19th. Before we begin, always remember to like this video. This tells your YouTube algorithm that you love these topics, and that you want to see more content like this. And if you enjoy our calming science documentaries, do not forget to subscribe and hit that notification bell so you never miss an upload. Now tell me in the comments, where are you listening from tonight? What time is it there? And here is my question for you. Do you believe 3i Atlas is a natural object, or do you think there is something more to this interstellar visitor? I'm always curious to hear your thoughts. The X-ray halo that should not exist. On the 26th of November 2025, a Japanese satellite turned its instruments toward a patch of sky in the constellation Virgo where something extraordinary was happening. The satellite was called XRISM, which stands for X-ray Imaging and Spectroscopy Mission, a collaboration between the Japanese Aerospace Exploration Agency, NASA, and the European Space Agency. Its target was an object that had entered our solar system 5 months earlier, an object that had already defied expectations at every turn, and now it was about to reveal something that no interstellar visitor had ever shown us before. For 17 hours straight, the Extend telescope aboard XRISM gathered photons from 3i Atlas. The observation window had been carefully calculated because XRISM has strict operational limits. It cannot point within 60 degrees of the Sun without risking damage to its sensitive detectors. 3i Atlas had only recently emerged from behind the Sun after passing through perihelion in late October, and this was the first opportunity to catch it in X-ray wavelengths. What the Japanese team found when they processed the data stopped them in their tracks. A faint glow extended outward from the comet's nucleus across an angular distance of 5 arc minutes. When you translate that into physical scale at the comet's distance, you get a structure stretching approximately 400,000 kilometers into space. To put that in perspective, the distance from Earth to the Moon is about 384,000 kilometers. This X-ray halo is larger than the gap between our planet and its only natural satellite. And here is what makes this so remarkable. We have never detected X-rays from an interstellar comet before. This is a first in the history of astronomy. Now you might wonder why X-rays from a comet are significant at all. After all, we have known since 1996, when comet Hyakutake surprised everyone, that comets in our own solar system can emit X-rays. The mechanism is well understood. When the solar wind, that constant stream of charged particles flowing outward from the Sun, collides with the gas surrounding a comet's nucleus, something called charge exchange occurs. Highly charged ions in the solar wind steal electrons from neutral atoms in the comet's coma. As those electrons settle into lower energy states, they release X-ray photons. It is a beautiful piece of physics, and it tells us about both the comet and the solar wind simultaneously. But 3i Atlas is not from our solar system. It formed around another star, possibly 7 billion years ago, billions of years before our own Sun even ignited. The ices locked in its nucleus have never been heated by our star until now. The materials sublimating off its surface carry chemical signatures from an entirely alien environment. And the question that haunted researchers was whether an interstellar comet would interact with our solar wind in the same way as local comets. or whether something fundamentally different would occur. The preliminary analysis suggests the X-ray emission is associated with a diffuse cloud of gas surrounding 3I Atlas. This aligns with earlier detections from the Webb Space Telescope and the Sphere-X Observatory, which mapped a massive carbon dioxide plume extending hundreds of thousands of kilometers from the nucleus. The comet is outgassing prodigiously, releasing approximately 129 kilograms of carbon dioxide every second, according to Webb measurements, along with smaller amounts of water and carbon monoxide. This river of gas provides the raw material for charge exchange with the solar wind, and now we are seeing the X-ray signature of that interaction in real time. But the XRISM team is being cautious. In their initial report published to the Astronomers' Telegram on December 3rd, they noted that instrumental effects could potentially mimic similar structures in the data. Vignetting, which is a gradual decrease in X-ray intensity toward the edges of the detector's field of view, and ordinary detector noise can both create features that look like extended emission. Further analysis is required to confirm that what they are seeing is genuinely astrophysical and not an artifact of the observation process. Science moves carefully, and extraordinary claims demand extraordinary verification. Yet if the detection holds up under scrutiny, and early indications suggest it will, we are witnessing something unprecedented. The X-ray spectrum itself may contain clues about elements in the comet's outflow. Charge exchange produces characteristic emission lines depending on which ions are involved. Excess X-ray emission at energies associated with carbon, nitrogen and oxygen ions has already been hinted at in the data. These are not random elements. These are the atoms that form the backbone of organic chemistry. These are the elements that make life possible. Think about what that means for a moment. An object that has travelled through the void between stars for billions of years, carrying frozen materials from a planetary system we will never visit, is now interacting with our sun's particle wind in a way that produces X-rays at energies tied to the elements of life. The comet is literally glowing with the signature of carbon, nitrogen, and oxygen as it races through our neighbourhood. It is as if 3I Atlas is broadcasting its chemical identity across electromagnetic wavelengths we have only recently learned to observe. The timing of this detection is remarkable for another reason. 3I Atlas reached perihelion, its closest approach to the Sun, on October the 29th at a distance of approximately 203 million kilometres. During that passage, it was hidden from Earth-based telescopes because it appeared too close to the Sun in our sky. We were blind precisely when the comet was being heated most intensely, when its activity should have peaked, when the most dramatic outgassing was occurring. Solar observing missions like Stereo and SOHO tracked it during that blackout period, watching its brightness surge far faster than models predicted. But detailed spectroscopy was impossible. Now the comet has swung around to the other side of its orbit and is racing back toward the outer solar system. It is still highly active, still venting gas and dust into space, and it will remain observable for several more months. The X-ray detection opens a new window into its behaviour. If charge exchange is producing the glow, then the strength and spectrum of the X-ray should change as the solar wind varies. There's a kind of conversation happening between our star and this ancient visitor, written in high-energy photons that we're only beginning to translate. I want you to hold that image in your mind. A comet older than Earth, possibly older than the Sun itself, surrounded by a halo of X-rays stretching farther than the distance to our moon, releasing chemicals that were locked in ice when our entire solar system was nothing but a cloud of gas and dust. Every photon that reaches our detectors carries information about conditions around a star that may no longer exist, about a planetary system we cannot see, about the raw materials that might have seeded life on worlds we will never know. The XRISM team has promised continued observations. As their data processing improves, we may learn exactly which elements dominate the X-ray emission. We may be able to compare the chemistry revealed by X-rays to the chemistry measured by infrared and radio telescopes. And we may discover that 3I Atlas is telling us something about the universality of life's building blocks that transforms our understanding of biology's place in the cosmos. There is something else worth considering here, something that connects to a broader pattern we have observed with 3I Atlas since its discovery. Every time astronomers have predicted how this object should behave based on our experience with solar system comets, it has surprised us. When Webb first looked at its composition in August, the carbon dioxide to water ratio turned out to be nearly 8-1, among the highest ever measured in any comet. When ground-based telescopes tracked its brightness approaching perihelion, it surged faster than standard models predicted. When observers expected its tail to point away from the Sun like every other comet, it developed a sunward anti-tail structure that defied easy explanation. And now, we have X-ray emission extending 400,000 kilometers into space, the first such detection from any interstellar object, revealing that whatever process is driving this comet's activity is powerful enough to create a high-energy glow visible across the electromagnetic spectrum. The pattern is consistent. 3I Atlas refuses to fit neatly into our existing categories. It demands new explanations at every turn. Some scientists see this as evidence that interstellar comets are simply more diverse than we expected. The galaxy is vast, and the conditions around other stars could produce icy bodies with wildly different compositions than what we find in our own solar system. If 3I Atlas spent billions of years bathing in cosmic radiation as it drifted between stars, that bombardment could have transformed its surface chemistry in ways we are only beginning to understand. A recent study suggests the comet may have developed a thick irradiated crust over its 7 billion-year journey, a crust whose properties no longer resemble the original materials deposited when the comet first formed. Others wonder if we are seeing something more unusual. The coincidences have accumulated, to a point where even mainstream astronomers are acknowledging that 3I Atlas presents mysteries worth taking seriously. Not necessarily evidence of anything artificial, but certainly evidence that our understanding of cometary behavior is incomplete. The X-ray halo is the latest data point in a growing file of anomalies, and science advances precisely by wrestling with observations that do not fit established theory. The XRISM observations will continue through the coming weeks. Additional data from their high-resolution X-ray spectrometer called Resolve may provide even more detailed chemical information if the emission is bright enough. Meanwhile, other telescopes are gathering their own measurements, building a comprehensive portrait of this visitor, before it fades into the outer solar system and eventually vanishes back into interstellar darkness. But the X-ray halo is only one piece of a much larger puzzle. Because while Japanese astronomers were processing their data from late November, another spacecraft had already captured images that revealed something even stranger about 3I Atlas, something that conventional comet science struggles to explain. When the European Space Agency's JUICE mission pointed its navigation camera at this interstellar wanderer, it found not one tail streaming behind the nucleus, but two distinct structures extending in different directions, and one of them appeared to be made of something entirely unexpected. 8 days until contact. As I record these words, the calendar shows December 11th, 2025. In precisely 8 days, on December 19th, 3I Atlas will reach its closest point to Earth. Now, before anyone feels a spike of anxiety, let me be absolutely clear about the geometry here. Closest is a relative term when we're talking about interstellar distances. The comet will pass approximately 1.8 astronomical units from our planet, which translates to roughly 170 million miles or 270 million kilometers. For reference, that is nearly twice the distance between Earth and the Sun. There is no danger. There is no impact scenario. The laws of orbital mechanics are unambiguous on this point, but proximity matters for observation. The closer an object is, the more light reaches our telescopes, the more detail we can resolve, and the more data we can extract before the visitor fades into the cosmic background. December the 19th represents a critical inflection point in our study of 3I Atlas. After that date, the comet will be heading outward, growing fainter with each passing week, its secrets increasingly difficult to pry loose from the signal noise. What we learn in the next few weeks may be all we ever learn about this particular messenger from another star. Right now, 3I Atlas is positioned in the constellation Virgo, visible in the pre-dawn sky for observers in the northern hemisphere. If you have access to a telescope with at least 8 inches of aperture and reasonably dark skies, you can see it for yourself. The comet currently shines at approximately magnitude 12, which puts it well beyond naked eye visibility, but within reach of serious amateur equipment. Through a telescope eyepiece, it appears as a fuzzy smudge with a brighter central condensation, its coma extending outward in a ghostly halo. Photographs with longer exposures reveal the tail structures that have caused so much excitement in recent days. The viewing geometry is actually improving as we approach the 19th. Today, on December 11th, the comet passes less than 2 degrees from the half-moon, which provides a convenient reference point for anyone trying to locate it. By December 12th, it will have moved to a position more than 90 degrees away from the Sun in our sky, making it accessible near midnight for many observers. The window is opening, and astronomers worldwide are preparing for what may be their best opportunity to gather data. NASA has effectively transformed the entire solar system into a distributed observatory for this event. The list of missions contributing observations reads like a who is who of space exploration. The Hubble Space Telescope continues to track the comet, with its Wide-Field Camera 3 providing high-resolution images of the coma and inner tail region. The James Webb Space Telescope is scheduled for additional infrared observations in December to monitor how the carbon dioxide-dominated coma evolves now that the comet is moving away from the Sun. The SphereX mission, an all-sky infrared surveyor launched earlier this year, has already contributed critical data on the comet's chemical fingerprint. But the observations extend far beyond Earth orbit. The Psyche mission, currently en route to a metal-rich asteroid of the same name, turned its multispectral imager toward 3I Atlas in September when the spacecraft passed within 33 million miles of the comet. Those images helped refine our understanding of the comet's trajectory with unprecedented precision. The Lucy mission, designed to study Jupiter's Trojan asteroids, captured the comet from 240 million miles away, providing a unique vantage point that ground-based telescopes cannot replicate. Mars has proven particularly valuable. The Mars Reconnaissance Orbiter and the ExoMars Trace Gas Orbiter both observed 3I Atlas during its close approach to the Red Planet on October 3rd, when the comet passed within 29 million kilometers of Mars. The HIRAS camera aboard MRO potentially captured images with a resolution of 30 kilometers per pixel, though NASA has been selective about which data they have released publicly. The Perseverance rover on the Martian surface also contributed to the observation campaign, adding yet another perspective to our growing archive of 3I Atlas imagery. Even solar observing missions have joined the effort. Stereo, SOHO, and the newer Punch mission all tracked the comet during its perihelion passage when it was invisible from Earth. Those spacecraft watched the space around the Sun continuously, and they caught 3I Atlas brightening dramatically as it swung through its closest solar approach. The Parker Solar Probe, humanity's closest emissary to our star, may have gathered data as well, though that has not been confirmed in public announcements. And then there is JUICE. The Jupiter Icy Moons Explorer, a European Space Agency mission launched in April 2023, is currently cruising through the inner solar system on a complex trajectory that will eventually deliver it to Jupiter in 2031. In early November, JUICE found itself in a remarkable position. The spacecraft was approximately 41 million miles from 3I Atlas, closer than any other operational probe at that moment, and it had a direct line of sight to the comet just days after perihelion, when activity was ramping up dramatically. The JUICE team activated 5 scientific instruments to study the interstellar visitor. Janus, the optical camera, MAGIS and UVS, spectrometers designed to analyze light across different wavelengths, SWI, a submillimeter wave instrument, and PEP, a particle detector that might sense material flowing off the comet. The spacecraft also turned its navigation camera toward 3I Atlas, capturing an image that would prove unexpectedly revealing. Here is where the story gets interesting. JUICE is currently using its main high-gain antenna as a heat shield to protect delicate instruments from solar radiation during its inner solar system traverse. That means data can only trickle back to Earth through a smaller medium-gain antenna at a fraction of the normal transmission rate. The full scientific dataset from those November observations will not arrive until February 2026. Mission controllers face a choice: wait months for the complete information, or take an early peek through a narrow straw. They chose to peek. The team downloaded just 1/4 of a single image from the navigation camera, a frame captured on November 2nd, 2025. Even in this low-resolution partial view, What they saw was extraordinary. 3I Atlas appeared surrounded by a bright glowing coma with not one but two distinct tail structures extending in different directions. The main tail, composed of electrically charged plasma gas, stretched toward the upper portion of the frame. A fainter secondary tail made of tiny solid dust particles trailed off toward the lower left. The comet was unmistakably active, brimming with energy from its recent solar encounter. Two tails is not unheard of for comets. In fact, many comets in our solar system display both a dust tail and an ion tail under the right conditions. The physics is straightforward. Solar radiation pressure pushes dust grains away from the nucleus in a curved path determined by the balance between gravity and light pressure. Meanwhile, the solar wind interacts with ionized gas molecules, accelerating them directly away from the sun in a straighter formation. The two forces act on different materials and produce visually distinct structures. But the clarity with which JUICE captured these features on 3I Atlas surprised researchers. They described the comet as looking extremely active, more so than they anticipated for an object that had only just emerged from perihelion. The coma blazed bright in the navigation camera image. The plasma tail showed clear definition. Even the fainter dust tail was visible in what amounts to a snapshot from a camera designed for spacecraft navigation, not cutting-edge comet science. What makes this significant is that 3I Atlas has been sending mixed signals about its tail throughout its journey. In some earlier observations, the comet appeared to have lost its tail entirely after rounding the sun. Conspiracy-minded observers seized on this, suggesting something unusual was happening. The reality turned out to be more mundane but equally fascinating. The apparent disappearance was a perspective illusion. The tail had not vanished. It was simply pointing almost directly away from Earth, hidden behind the bright coma like looking at a flashlight beam head-on. As the geometry shifted, the tail structure revealed itself again. The JUICE image confirms that 3I Atlas is behaving like a vigorous active comet, exactly what you would expect from an icy body that just experienced its first intense solar heating in billions of years. The cryovolcanic eruptions that other researchers have documented, the ice volcanoes blasting material off the surface, are feeding both the gaseous coma and the solid dust population that forms the secondary tail. Everything we see is consistent with a natural object undergoing dramatic thermal stress. And yet, questions remain. The exact composition of those tails, the ratio of dust to gas, the size distribution of particles, the precise chemistry of the ionized material, all of these details await the full JUICE dataset in February. When those observations arrive, they will represent the closest detailed view of an interstellar comet ever obtained by a spacecraft. JUICE was not designed with interstellar visitors in mind. Its instruments were built to study Jupiter's icy moons Ganymede, Callisto, and Europa. The fact that it happened to be in position to observe 3I Atlas during one of the comet's most active phases is pure serendipity, a gift of orbital mechanics that astronomers are scrambling to exploit. The countdown continues. 8 days until closest approach, roughly 10 weeks until the JUICE data arrives. And somewhere out there in the darkness between worlds, 3I Atlas races onward at 130,000 miles per hour, carrying its frozen cargo of chemicals and mysteries toward a brief encounter with our planet before vanishing into the interstellar void forever. Every observation matters, every photon counts. The clock is ticking, and the scientific community knows that what we fail to measure now will be lost for all of human history. But measurements have already revealed something that transforms our understanding of what this comet is carrying. Because the chemistry of 3I Atlas is unlike anything we have encountered before. The concentrations of certain molecules directly tied to the origins of life, have shattered records that stood for decades. And what NASA announced this week about methanol and hydrogen cyanide could rewrite the textbooks on how life's building blocks are distributed across the galaxy. Life's recipe. Written in alien ice high in the Chilean Andes, at an altitude of 5,000 meters where the air is thin and the sky is impossibly dark, 66 radio antennas work together as a single instrument. This is ALMA, the Atacama Large Millimeter Submillimeter Array, one of the most powerful telescopes ever built for studying the cold universe. While optical telescopes see light from stars and galaxies, ALMA detects radio waves emitted by molecules in space, the chemical fingerprints of matter scattered across cosmic distances. and in late 2025, ALMA turned its attention to 3I Atlas, with results that are now sending ripples through the astrobiology community. A team led by Martin Cordner at NASA's Goddard Space Flight Center used ALMA to observe the comet on multiple occasions between August and October as it approached perihelion. They were hunting for specific molecules, compounds that might reveal something about the chemistry of the planetary system where 3I Atlas originally formed. What they found exceeded their expectations in ways that are difficult to overstate. The comet is releasing methanol at a rate of approximately 40 kilograms per second. Methanol, the simplest alcohol molecule, consists of one carbon atom, 4 hydrogen atoms, and one oxygen atom arranged in a specific configuration. It might not sound impressive until you consider the proportions. Roughly 8% of all the vapour streaming off 3I Atlas is methanol. That's approximately 4 times higher than what we typically measure in comets from our own solar system. The production rate is among the most enriched values ever recorded for any comet, solar system or otherwise. But methanol was not alone. ALMA also detected hydrogen cyanide emanating from the comet's nucleus at rates between 1/4 and 1/2 kilogram per second. Hydrogen cyanide is a molecule with a complicated reputation. On one hand, it is a deadly poison in sufficient concentrations, the active component in certain chemical weapons historically used in warfare. On the other hand, it is a critical precursor for the synthesis of amino acids and nucleic acid bases, the molecular building blocks of proteins and DNA. Life as we know it could not exist without the chemistry that hydrogen cyanide enables. The ratio of methanol to hydrogen cyanide in 3I Atlas turns out to be extraordinary. According to analysis by Harvard astronomer Avi Loeb, this ratio is among the highest ever observed in any comet, second only to the anomalous solar system comet C 2016 R2 discovered by Pan-STARRS. That earlier comet was considered a bizarre outlier, a freak of nature whose extreme chemistry defied easy explanation. Now 3I Atlas has arrived from another star system entirely, and it shows similar enrichment patterns. The coincidence demands explanation. Let me put this in perspective. When Cordner and his team looked at comets in our own solar system, molecules like hydrogen cyanide and methanol appear only at trace abundances. They are present but not dominant, minor ingredients in a recipe dominated by water ice. Here we see that in this alien comet, they are extraordinarily abundant. The chemistry is not merely different, it is different in a specific direction, toward molecules that participate in prebiotic synthesis, toward compounds that laboratory experiments have shown can lead to amino acids and nucleobases under the right conditions. The ALMA data revealed another important detail. Methanol is appearing not only from the comet's solid nucleus, but also from the extended coma itself. Icy grains floating in the cloud of gas and dust surrounding the nucleus are releasing their own methanol as they warm in sunlight. This distributed source suggests that the comet's volatile inventory is spread throughout its structure, not concentrated in a single core region. The entire body seems to be a frozen reservoir of complex chemistry, waiting to be unleashed. Now I want to be careful here because this finding has generated sensational headlines that sometimes outpace the science. Some reports have breathlessly announced that 3I Atlas is carrying the ingredients for life, as if the comet might seed our planet with alien organisms. That is not what the data shows. What the data shows is that an object from another star system contains elevated concentrations of molecules that are relevant to the chemistry of life. That is different from saying it contains life, or could create life, or was sent to bring life. The distinction matters, but the finding is nonetheless profound. One of the great questions in astrobiology is whether the chemical conditions that gave rise to life on Earth are common or rare throughout the galaxy. If our solar system is unusual, if the particular mix of elements and molecules present in our primordial environment was a cosmic accident, then life might be exceedingly rare. If, on the other hand, those conditions are typical, if planets throughout the Milky Way have access to similar chemical building blocks, then life might be common. 3I Atlas provides a data point. Here is an object that formed around a completely different star, possibly 7 billion years ago, possibly in the thick disk of the Milky Way, where stars are older and chemically distinct from our neighbourhood. And despite those different origins, it carries methanol and hydrogen cyanide in abundance. It suggests that the raw materials for prebiotic chemistry are not unique to our corner of the cosmos. They are out there, frozen into comets and asteroids and icy bodies drifting between the stars, waiting to be delivered to young planets wherever gravitational encounters send them. This connects to a theory that has been debated for decades. Panspermia, in its various forms, proposes that life or its precursor chemicals might spread between worlds carried by objects like comets and meteorites. The idea has often been dismissed as speculative, but discoveries like this one lend it a certain plausibility. We know that complex organic molecules can survive the harsh conditions of interstellar space. We know that comets can deliver material to planetary surfaces. We know that early Earth was bombarded by such objects during the late heavy bombardment period roughly 4 billion years ago. The question has always been whether those deliveries contributed meaningfully to the chemistry that eventually produced living cells. 3I Atlas cannot answer that question definitively. But it demonstrates that the delivery mechanism exists and that the cargo can include molecules directly relevant to life's origins. If one interstellar comet carries this much methanol and hydrogen cyanide, how many others might be drifting through the galaxy with similar loads? How many have impacted planets over the billions of years since star formation began? The numbers are staggering to contemplate. There is another angle worth considering. The specific way that methanol and hydrogen cyanide are being released from 3I Atlas tells us something about the comet's internal structure. The fact that methanol appears both from the nucleus and from coma grains suggests that the icy body is not homogeneous. Different regions may have different compositions. The nucleus might be layered or patchy, with pockets of distinct chemistry that sublimate at different rates as solar heating penetrates the surface. Some researchers have proposed that this patchiness could indicate a high metal content within the comet. When water ice melts and interacts with iron-bearing minerals, chemical reactions can produce methanol. If 3I Atlas contains iron compounds in its rocky core, the warming it experienced at perihelion might have triggered exactly this kind of reaction, generating methanol not just from primordial ices, but from active chemistry happening in real time as we watch. This would make 3I Atlas even more interesting as a laboratory for studying cometary processes. We would be observing not just the release of ancient frozen materials, but ongoing, chemical transformation driven by solar energy. The comet would be cooking as it flies, producing new compounds from old ingredients in ways that mirror processes that might have occurred on early Earth. The ALMA team has more observations planned. As 3I Atlas continues its outward journey, they will track how methanol and hydrogen cyanide production rates change with distance from the Sun. The power law relationship they have already measured, showing methanol increasing steeply as the comet approached the Sun, will be tested in reverse as the heating diminishes. If the chemistry is purely sublimation-driven, production should decline predictably. If more complex processes are involved, surprises may await. Meanwhile, other research groups are pursuing complementary measurements. The Webb telescope's infrared instruments can detect different molecular species than ALMA's radio receivers. Ground-based observatories are monitoring the comet's visible spectrum for emission lines that indicate specific atoms and radicals in the coma. The full chemical inventory of 3I Atlas is still being assembled, and every new detection adds another piece to the puzzle. What emerges from this collective effort is a portrait of an object unlike anything we have studied before. Not because it is artificial, not because it violates physics, but because it formed in conditions we have never sampled directly. Every comet from our solar system, no matter how unusual, shares a common origin in the disk of gas and dust that surrounded our young sun. 3I Atlas does not share that origin. It is a genuine outsider, an immigrant from distant reaches, and its chemistry reflects wherever it came from. When astronomers say that this comet contains ingredients for life, they are not making a mystical claim. They are reporting measurements of molecules that participate in well-understood reactions. Methanol can be converted into formaldehyde, which is a precursor to sugars. Hydrogen cyanide can polymerize into adenine, one of the 4 nucleobases in DNA. These are not hypothetical pathways. They are reactions that have been demonstrated in laboratories, reactions that could have occurred in warm little ponds on early Earth, reactions that might be occurring on other worlds right now. 3I Atlas is a messenger. The message it carries is written in molecules, and the text says that the chemistry of life is not a local invention. It is a cosmic inheritance, spread across the galaxy in frozen packages that occasionally pass through solar systems like ours, dropping their cargo on any planet lucky enough to intercept them. We are reading that message now, in the fading light of an alien comet's tail, and what we are learning suggests that we may have company in the universe. Not necessarily intelligent company, but living company, microbial company, chemical company, that shares our molecular ancestry, even if we will never meet. But the chemistry is not the only mystery surrounding 3I Atlas. Because even as ALMA was measuring methanol and hydrogen cyanide, other observers were documenting behaviour that standard comet physics does not easily explain. The ice volcanoes erupting from this object's surface follow patterns that some researchers find perplexing, and what they reveal about the comet's internal dynamics challenges assumptions we have held for decades. The twin tails. They almost missed the European Space Agency faced a dilemma in early November 2025. Their JUICE spacecraft had just completed its observation window for 3I Atlas, gathering what might be the most valuable close-range data ever collected on an interstellar object. 5 scientific instruments had been pointed at the comet during its most active phase, capturing spectra and images and particle measurements that could reveal secrets about its composition and behaviour. But all that precious data was trapped aboard a spacecraft that could only whisper to Earth. The problem was thermal. JUICE was designed to survive the brutal environment around Jupiter, where temperatures can swing from extreme cold in shadowed regions to intense heat, when instruments face the giant planet's reflected sunlight. To reach Jupiter, the spacecraft must first complete a complex series of gravitational assists that swing it through the inner solar system. During these passages close to the Sun, engineers needed to protect delicate electronics from overheating. Their solution was elegant but limiting. They oriented the spacecraft so that its main high-gain antenna faced the Sun, using the large dish as an improvised heat shield. This configuration kept JUICE safe but created a communication bottleneck. With the high-gain antenna pointed sunward, only a smaller medium-gain antenna could transmit to Earth, and it could only manage a trickle of data compared to the fire hose that the main antenna provides. The full science payload from the 3I Atlas observations would need to wait until February 2026, when orbital geometry allowed the spacecraft to reorient safely. Months of delay for what might be historically significant measurements. The JUICE mission team was not willing to wait blindly. They wanted at least a glimpse of what their spacecraft had captured, so they made a calculated decision. They would download just a fraction of a single image from the navigation camera, enough to confirm that observations had succeeded and to provide a tantalizing preview of the scientific bounty to come. On December 4th, ESA released that partial image to the world. What it showed silenced skeptics and energized researchers in equal measure. 3I Atlas blazed bright in the frame, its nucleus surrounded by a luminous coma that extended well beyond the central condensation. But the real revelation was the tail structure. 2 distinct features emerged from the comet, stretching in different directions against the starfield background. A plasma tail composed of ionized gas pointed roughly upward in the image orientation, following the direction pushed by the solar wind. A fainter dust tail made of solid particles curved away toward the lower left, its trajectory shaped by the gentler pressure of sunlight on microscopic grains. The dual tail structure confirmed that 3I Atlas was behaving exactly like a vigorous comet should. When solar heating causes ices to sublimate from a comet's nucleus, 2 distinct populations of material enter the coma. Gas molecules become ionized by solar ultraviolet radiation and interact with the magnetized solar wind, accelerating away from the Sun in a relatively straight stream. Dust particles released along with the gas feel a weaker force from radiation pressure and follow curved paths that depend on their size, with smaller grains pushed more strongly than larger ones. The combination produces the classic two-tail appearance that astronomers have documented in dozens of solar system comets. But documenting dual tails in an interstellar comet carries different significance. 3I Atlas formed around another star under conditions we can only guess. The ices locked in its nucleus condensed from a protoplanetary disk with different chemistry than our own. The dust grains mixed into that ice might have different compositions, different size distributions, different optical properties than materials we find in local comets. Seeing a familiar tail structure tells us that despite those different origins, the basic physics of cometary activity transcends stellar boundaries. Sunlight and solar wind affect interstellar ices the same way they affect local ones. The processes are universal. The image also showed something the JUICE team described as intense activity. The coma appeared brighter and more extended than might have been expected for the observation timing. Remember, this image was captured on November 2nd, just 4 days after perihelion, when 3I Atlas was still processing the thermal shock of its closest solar approach. The nucleus was essentially shedding material at maximum rate, its surface erupting with gas and dust as buried ices reached sublimation temperatures for the first time in possibly billions of years. Consider what that heating episode represented. 3I Atlas spent most of its existence drifting through the coldest environment imaginable, the space between stars where temperatures hover just a few degrees above absolute zero. Whatever ices formed when the comet first coalesced have remained frozen ever since, locked in crystalline structures that preserved their original chemistry through cosmic timescales. Then, in the span of a few months, solar radiation penetrated the surface and began warming those ancient deposits. Volatile compounds started transforming from solid to gas, expanding outward at speeds of hundreds of meters per second, carrying dust, grains along in the flow. The comet essentially exploded in slow motion, venting its stored inventory into space. The JUICE image captured that explosive release mid-flight. The brightness of the coma reflects the sheer volume of material entering the vacuum around the nucleus. The extent of the tail structures shows how far that material has travelled in the days since release. We are looking at a snapshot of destruction and revelation simultaneously, an ancient object giving up secrets it has held since before Earth existed. There is a poignant dimension to this observation. JUICE was never meant to study comets. Its scientific payload was designed for Jupiter's icy moons, for detecting subsurface oceans and mapping geological features and sniffing magnetic fields. The navigation camera that captured this image exists primarily to help the spacecraft orient itself during complex maneuvers. Yet here was JUICE, still years from its destination, using improvised capabilities to document something no spacecraft has ever seen so clearly. An interstellar comet in full activity just days after perihelion. The serendipity is remarkable. If 3I Atlas had arrived a few years earlier or later, JUICE would not have been in position. If the comet's trajectory had been slightly different, the closest approach distance would have been too large for meaningful observation. If the thermal constraints had been slightly more severe, no image download would have been possible at all. A chain of coincidences aligned to give us this glimpse, and scientists are treating it as a gift from the cosmos. What the full dataset will reveal remains to be seen. When February arrives and the complete observations finally reach Earth, researchers will have spectra from MAGIS and UVS that could identify specific molecules in the coma with far greater precision than the navigation camera allows. The SWI submillimeter instrument may have detected water vapour and other volatiles. The PET particle detector might have sensed material from the comet's extended environment passing by the spacecraft. Each instrument contributes a different puzzle piece, and the assembled picture could transform our understanding of interstellar visitors. But even the partial image has advanced the science. It proved that 3I Atlas remained active through perihelion, dismissing fears that the solar heating might have fragmented or exhausted the nucleus. It confirmed the presence of both gas and dust outflow, essential for understanding the comet's composition. It demonstrated that an interstellar object can display the classic cometary morphology that we associate with local icy bodies, and it provided a reference point against which ground-based and other space-based observations can be calibrated. The social media response to the JUICE image was immediate and intense. Within hours of ESA's release, the picture was circulating on every platform, accompanied by commentary ranging from sober scientific analysis to wild speculation about alien origins. Some observers noted that the twin-tail structure looked nothing like a comet should, though of course it looked exactly like what comets display when conditions favour dual-tail formation. Others claimed to see unusual features in the coma that might indicate artificial structures, though image processing experts quickly showed those features were artifacts of the partial download and enhancement. The alien hypothesis refuses to die despite mounting evidence for natural origins. Every new observation of 3I Atlas gets filtered through a lens of suspicion by those who want to believe we are being visited. The dual tails become evidence of directional propulsion. The bright coma becomes an energy shield. The activity levels become deliberate signalling. It would be amusing if it were not distracting from the genuine wonder of what we are witnessing, because what we are witnessing is wonder enough. An object from another star carrying chemistry from an alien protoplanetary disk is racing through our solar system close enough that a spacecraft designed for Jupiter could photograph it with a navigation camera. The image shows tail structures that demonstrate universal physics operating across stellar boundaries. The brightness shows activity levels that suggest abundant volatiles surviving billions of years of cold storage. We do not need aliens to make this extraordinary. It is extraordinary on its own merits. The JUICE team deserves credit for their quick thinking and scientific opportunism. When 3I Atlas was discovered in July, mission planners rapidly assessed whether observation would be possible, given the spacecraft's trajectory and orientation constraints. They determined that a window existed in early November, and they seized it despite the data transmission limitations they knew they would face. The partial image was their proof of concept, their advertisement for the riches stored aboard until February allows full retrieval. Meanwhile, other spacecraft continue their own campaigns. Hubble has captured multiple images since 3I Atlas emerged from behind the Sun, tracking changes in coma morphology and tail extent. Webb is preparing follow-up infrared observations to monitor the evolution of carbon dioxide and other volatiles as the comet recedes from the Sun. Ground-based telescopes around the world are gathering photometric and spectroscopic data every clear night. The coming weeks represent a coordinated global effort to extract maximum scientific value before distance claims our visitor. And as mentioned earlier, the data from those observations keeps revealing surprises. Because the twin tails that JUICE photographed are fed by processes occurring on the comet's surface, processes that researchers are now calling cryovolcanism, and the pattern of those eruptions suggests that 3I Atlas is not simply heating uniformly. Something more interesting is happening beneath the surface, and it is leaving visible traces in the spiral jets that extend toward the Sun. Ice volcanoes erupting from another star. In the early December, a team of European researchers published observations that added yet another layer of complexity to our understanding of 3I Atlas. Josep Trigo Rodriguez, from the Institute of Space Sciences in Barcelona, and his collaborators had been monitoring the comet from the Montseny Observatory, tracking changes in its appearance over weeks of careful observation. What they documented was not merely outgassing in the general sense, but something more structured, more dramatic, more reminiscent of volcanic activity than passive sublimation. They observed spiral jet features extending from the nucleus of 3I Atlas, rotating patterns of enhanced brightness that indicated material being ejected from specific locations on the comet's surface. These were not diffuse plumes spreading uniformly in all directions. These were collimated streams emerging from discrete source regions, maintaining coherence over distances of hundreds of thousands of kilometers, before gradually dispersing into the broader coma. The researchers interpreted these features as evidence of cryovolcanism, ice volcanoes erupting on the surface of an interstellar object. The term cryovolcanism might sound exotic, but the phenomenon is well documented in our solar system. On Saturn's moon Enceladus, geysers of water ice spray hundreds of kilometers into space from fractures near the South Pole. On Neptune's moon Triton, nitrogen ice erupts in plumes that have been photographed by passing spacecraft. Even on Pluto, there is evidence of past cryovolcanic activity in the form of strange mountainous structures that defy easy explanation. Cold bodies with volatile ices can experience eruptions just as rocky bodies with molten rock experience traditional volcanism. The physics is similar even if the materials differ. What drives cryovolcanism on a comet? The basic mechanism involves subsurface heating. As solar radiation warms the outer layers of a comet's nucleus, heat conducts inward toward deeper ices that have remained frozen. When those buried volatiles reach their sublimation temperature, they transform directly from solid to gas, building pressure beneath the surface. If that pressure finds a weak point, a crack or fissure or porous region, the gas escapes explosively, carrying dust and ice particles along with it in a focused jet. The rotation of the comet's nucleus adds another dimension. As the body spins, different surface regions cycle through periods of illumination and shadow. A cryovolcanic vent on the day side might erupt vigorously as the sun heats it, then quiet down as rotation carries it into darkness. Hours later, As that region swings back into sunlight, eruption resumes. The result is a periodic pattern of activity tied to the rotation period of the nucleus. Observations of 3 I-Atlas suggest exactly this kind of behaviour. The spiral jet structures documented by the Spanish team appear to trace out arcs consistent with material being ejected from a rotating source. As the nucleus spins, the jets sweep through space like water from a garden hose wielded by a twirling child. The spiral pattern frozen into photographs is a record of that rotational motion captured over the exposure time of the image. This means we can potentially measure the rotation period of 3I Atlas from its jet patterns. If the spirals complete a certain fraction of a turn over a known time interval, the full rotation rate follows from simple geometry. Early estimates suggest the nucleus may rotate with a period of several hours, though the analysis is complicated by the three-dimensional structure of the jets and uncertainties in viewing angle. More observations over the coming weeks should refine these estimates. The location of the eruption sources is equally informative. Cryovolcanic vents do not appear randomly on a comet's surface. They develop where subsurface ice deposits exist and where pathways allow released gas to escape. If 3I Atlas shows jets emerging from consistent locations tied to its rotation, that tells us something about the internal structure of the nucleus. Certain regions are ice-rich and actively venting. Other regions may be depleted or blocked by less volatile materials. Some researchers have proposed that the jet activity on 3I Atlas is unusually vigorous compared to typical solar system comets. The comet brightened faster than expected as it approached perihelion, suggesting either larger than normal gas production rates or unusual scattering properties in the ejected material. The ice volcanoes might be tapping reservoirs of hypervolatile compounds, substances like carbon dioxide or carbon monoxide that sublimate at lower temperatures than water ice, and thus become active farther from the Sun. We already know from Webb telescope observations that 3I Atlas has an extremely high carbon dioxide to water ratio in its coma. The carbon dioxide ice buried in the nucleus would reach sublimation temperature well before water ice as the comet approached the Sun. This early activation could explain the rapid brightening that surprised observers. It could also explain why the cryovolcanic activity appeared so intense. The erupting material was dominated by carbon dioxide gas, which expands more energetically than water vapor under the same conditions. There is another possibility that some researchers are beginning to consider. The cryovolcanism on 3I Atlas might be accessing primordial materials that have never been heated before, not even when the comet first formed. During the billions of years this object spent in interstellar space, cosmic ray bombardment gradually transformed its outer layers through radiation chemistry. That processing created an irradiated crust, a shell of altered material surrounding the pristine interior. When solar heating penetrates through that crust and reaches the unchanged ices beneath, the contrast in properties could trigger especially violent eruptions. The pristine interior might contain volatile compounds in higher concentrations than the processed crust. The interface between altered and unaltered layers might provide natural pathways for gas escape. The entire structure of the comet might be set up for dramatic activity once sufficient heat arrives. This model would explain why 3I Atlas seemed to wake up so suddenly as it approached the Sun. For months after discovery, the comet showed only modest activity, a faint coma that grew slowly as distance decreased. Then, as perihelion approached and solar heating intensified, the activity surged. The cryovolcanic eruptions may have punched through the radiation-processed crust, suddenly venting materials that had been sealed for eons. The comet was not just heating up. It was breaking through a shell that had accumulated during its long interstellar exile. The implications for understanding interstellar objects are significant. If 3I Atlas is typical of such visitors, then all interstellar comets might arrive with irradiated crusts that initially mask their volatile content. They would appear inactive or weakly active until solar heating breached the outer layers, at which point the interior would erupt spectacularly. This could explain why 1EU showed so little cometary behaviour, despite displaying non-gravitational acceleration consistent with outgassing. Perhaps its irradiated crust was thick enough that solar heating during its brief passage never penetrated to pristine ices. Perhaps any activity was confined to small regions where the crust was thinner. 2 Borisov, the second interstellar object and the first confirmed interstellar comet, showed clear cometary activity, including cyanide and diatomic carbon emissions. But Borisov was discovered earlier in its approach and observed for longer, giving researchers more opportunity to catch it in an active state. Even so, its activity was considered somewhat muted compared to typical solar system comets at similar distances. The irradiated crust model might apply there as well, with Borisov's eruptions limited by a partially intact outer shell. 3I Atlas, by contrast, seems to have experienced dramatic breakthrough events. The ice volcanoes documented in recent weeks represent the nucleus literally excavating itself, exposing fresh material to solar heating and ejecting the products into space. Each eruption removes more of the processed crust and opens new pathways for subsurface volatiles to escape. The comet is peeling itself like an onion, layer by layer, revealing an interior that has been hidden since long before our solar system existed. What we are watching is archaeology on a cosmic scale. The materials venting from 3I Atlas date from an era we cannot access any other way. They formed in a protoplanetary disk around a star that may have died billions of years ago. They were frozen into a comet that was ejected into interstellar space by gravitational interactions we will never reconstruct. They travelled through the galaxy for longer than Earth has existed, passing through regions of space we have not mapped, accumulating radiation damage and chemical changes along the way. And now, briefly, those materials are being liberated where we can study them. The cryovolcanic jets are the delivery mechanism. Each spiral plume carries molecules that tell a story about distant origins and long journeys. Each particle of dust that enters the coma represents a fragment of another world, literally a piece of alien real estate floating through our neighbourhood. We cannot touch these samples or collect them in laboratories, but we can analyse the light they scatter and the wavelengths they absorb and emit. We can read their composition remotely, inferring what they are made of from the spectral fingerprints they leave in our instruments. That reading continues around the clock as observatories worldwide monitor 3I Atlas. The ice volcanoes are still erupting, still feeding the coma and tails that make this comet such a striking sight. How long the activity will continue depends on factors we cannot predict with certainty. The reservoir of subsurface volatiles is unknown. The thermal structure of the nucleus is unknown. The thickness and distribution of the irradiated crust is unknown. Each variable affects how long the comet will remain active and how dramatically it will behave. But one thing seems certain. 3I Atlas is giving us a show that no previous interstellar visitor has provided. The combination of its large size, its volatile-rich composition, and its relatively close approach to both Sun and Earth has created ideal conditions for observation. The ice volcanoes are part of that show, a spectacular reminder that even objects billions of years old can come alive when circumstances change. And speaking of coming alive, there is another aspect of 3I Atlas that continues to puzzle researchers. The comet's colour is wrong. When astronomers first began tracking this object, it displayed a reddish hue consistent with organic rich surfaces exposed to cosmic radiation. Then something changed. The comet turned green, displaying fluorescence that typically indicates the presence of diatomic carbon molecules. But spectroscopic analysis says those molecules are absent or nearly so. The green glow has no obvious source, and explaining it has become one of the more intriguing mysteries surrounding our interstellar guest. The green glow without a source. September 7th, 2025 was an unusual night for astronomy. Total lunar eclipse was underway, plunging the moon into Earth's shadow and temporarily removing its glare from the night sky. For observers studying faint objects, a lunar eclipse is a gift. The darkened sky reveals details that are normally washed out by moonlight, allowing deeper exposures and more sensitive measurements. In Namibia, astrophotographers Gerald Riemann and Michael Jaeger had positioned their equipment to exploit exactly this opportunity. Their target was 3I Atlas, and what they captured would ignite a debate that continues to this day. The images showed the comet surrounded by a distinct blue-green glow. The coma, that fuzzy envelope of gas and dust surrounding the nucleus, displayed a colour that immediately stood out from the background stars. The green hue was unmistakable, extending across approximately 2.5 arc minutes of sky with a visible tail stretching behind. Under the darkened eclipse conditions, Riemann and Jaeger had captured something that previous observations had only hinted at. 3I Atlas was glowing green. For comets in our solar system, a green glow is commonplace and well understood. The colour comes from a molecule called diatomic carbon, written as C2 in chemical notation. Diatomic carbon consists of two carbon atoms bonded together, a simple but important compound that forms when larger carbon-bearing molecules are broken apart by solar ultraviolet radiation. When diatomic carbon molecules absorb sunlight and then re-emit that energy, they fluoresce at specific wavelengths that our eyes perceive as green. The process is called resonance fluorescence, and it paints many comets with that characteristic emerald tinge as they approach the sun. So observing green fluorescence from 3I Atlas should have been unremarkable. Another comet, another green glow, another confirmation of basic cometary physics. But there was a problem. Spectroscopic observations of 3I Atlas had failed to detect significant amounts of diatomic carbon. A team led by Luis Salazar Manzano at the University of Michigan had analysed the comet's spectrum and found it to be severely depleted in carbon chain molecules. 3I Atlas showed some of the lowest C2 and C3 abundances ever measured in any comet. It was, in their terminology, among the most carbon chain depleted comets known. This created a paradox. The comet was glowing green, but the molecule that should cause green fluorescence was absent or nearly so. Something else had to be responsible for the colour, but what? The spectroscopic evidence pointed one direction while the photographic evidence pointed another. Either the spectroscopy was missing something, or the green glow had a different origin than anyone expected. Let me walk through the scientific puzzle here, because it illustrates how discovery works at the frontier of knowledge. When we observe a comet's spectrum, we are seeing light at specific wavelengths that correspond to specific molecular transitions. Each type of molecule has a unique spectral fingerprint, a pattern of emission and absorption lines that identifies it, as surely as a barcode identifies a product. If diatomic carbon were present in the coma in significant quantities, we should see its characteristic spectral features. The fact that those features are weak or absent tells us the molecule is not there in abundance. Yet the green colour is real. The photographs are not lying. The coma genuinely appears green to cameras sensitive to visible light wavelengths. How can this be? Several possibilities have been proposed. The first is that diatomic carbon is present but in unusual conditions that make it difficult to detect spectroscopically, while still allowing it to fluoresce visibly. Perhaps the molecules are concentrated in a thin shell or specific region of the coma where their spectral signal is diluted by other materials. Perhaps the viewing geometry or solar illumination angle affects how strongly the emission lines appear in our spectra. This explanation preserves the standard model of cometary green fluorescence while invoking observational complications. The second possibility is more intriguing. Perhaps a different molecule is responsible for the green glow. While diatomic carbon is the usual suspect, other compounds can also fluoresce at similar wavelengths under the right conditions. Researchers are exploring whether any of the molecules known to be present in 3I Atlas, including carbon dioxide, cyanogen, and various organic compounds, might produce green emission through mechanisms not typically seen in solar system comets. The alien chemistry of this interstellar visitor might include fluorescence pathways that our local comets do not exhibit. The third possibility is the most challenging. Perhaps the green colour is not fluorescence at all, but scattered light from dust particles with unusual optical properties. If the dust grains in the coma of 3I Atlas have compositions or size distributions that preferentially scatter green wavelengths, the overall colour could appear green without any molecular fluorescence being involved. This would represent a fundamentally different explanation that shifts attention from gas chemistry to dust mineralogy. Distinguishing between these possibilities requires additional observations and careful analysis. Researchers need spectra at multiple wavelengths and from multiple viewing geometries. They need measurements of the dust grain properties through polarimetry and thermal emission studies. They need time series data showing how the green colour evolves as the comet moves through different solar illumination conditions. The mystery cannot be solved with a single observation. It requires the kind of comprehensive campaign that astronomers are currently conducting. Adding to the complexity, 3I Atlas has changed colour multiple times during its passage through the inner solar system. When first observed after discovery in July, The comet displayed a reddish hue, typical of objects whose surfaces have been processed by cosmic radiation. That red colour comes from complex organic molecules created when energetic particles bombard simple ices over billions of years. It was exactly what researchers expected for an interstellar visitor with an ancient irradiated crust. Then, as the comet approached the Sun and activity increased, the colour shifted. Some observers reported a transition from red to green, suggesting that fresh material being exposed by cryovolcanic eruptions had different optical properties than the processed surface. Others noted colour variations across different parts of the coma, with the inner regions showing different hues than the outer envelope. The comet seemed to be displaying multiple colours simultaneously, like a celestial mood ring responding to solar heating. Harvard astronomer Avi Loeb linked the colour change to the steep rise in cyanogen production measured by the Very Large Telescope in late August. Cyanogen is a molecule containing carbon and nitrogen that can fluoresce under solar illumination. Its emission is typically violet or blue rather than green, but under certain conditions interactions between cyanogen and other molecules might produce unexpected colours. Loeb suggested that the rapidly increasing cyanogen abundance was somehow connected to the green appearance, though the exact mechanism remained unclear. The chemistry gets even stranger when you consider what else has been detected in the coma of 3I Atlas. Webb telescope observations found carbonyl sulfide, a molecule containing carbon, oxygen, and sulfur that is rarely detected in comets. The high carbon dioxide abundance is anomalous by any standard. The methanol and hydrogen cyanide levels measured by ALMA are among the highest ever recorded. This is not a typical comet by any measure. Its chemical inventory is exotic, drawn from materials that formed under conditions very different from our solar system. Perhaps the green glow is simply another manifestation of that exotic chemistry. Perhaps 3I Atlas contains fluorescent compounds we have not identified because we have never encountered them in local comets. The molecule responsible might be common around the comet's parent star but rare or absent in our own neighbourhood. We would have no baseline for recognising it, no template spectrum to compare against, no theoretical prediction of its fluorescence properties. We would see the green colour and be baffled by it because our reference library is too limited. This is humbling to consider. Despite centuries of studying comets and decades of spacecraft missions and thousands of spectroscopic observations, we may be unprepared for the diversity of chemistry that interstellar visitors can display. Our expertise is local, our knowledge is parochial. When something truly foreign arrives, it can show us colours we do not understand using molecules we have not catalogued. The December 19th closest approach offers an opportunity to gather more data on this mystery. As 3I Atlas comes within 1.8 astronomical units of Earth, it will be better positioned for spectroscopic study than at any time since emerging from solar conjunction. High-resolution spectrographs at major observatories are scheduled to analyse its light in unprecedented detail. If a specific molecule is responsible for the green glow, we may finally identify it. If the explanation lies in dust properties, we may detect the signatures of unusual mineralogy. One way or another, the mystery should move toward resolution. But mysteries have a way of multiplying when interstellar objects are involved. Even as astronomers puzzled over the green colour, radio telescopes were detecting signals from 3I Atlas that required their own explanation. The first radio emission ever recorded from an interstellar object came not from alien transmissions, but from chemical processes that reveal yet another dimension of this comet's complex character. The hydroxyl radicals streaming off its surface are telling a story about water and sunlight and the ancient ices of another star system. Radio whispers from an ancient traveller. On October 24, 2025, astronomers at the South African Radio Astronomy Observatory pointed an array of 64 radio dishes toward a patch of sky where 3I Atlas was racing through its closest approach to the Sun. The Meerkat telescope, located in the Karoo region of South Africa, is one of the most sensitive radio instruments on the planet. Its dishes work together as a single enormous antenna capable of detecting faint whispers from across the cosmos. And on that October night, Meerkat heard something from our interstellar visitor. The detection came in the form of absorption lines at very specific radio frequencies 1665 MHz and 1667 MHz. These frequencies are well known to radio astronomers because they correspond to transitions of the hydroxyl radical, a molecule consisting of one oxygen atom and one hydrogen atom written as OH. When hydroxyl molecules absorb radio waves from a background source at these precise frequencies, they leave a characteristic notch in the observed spectrum. Meerkat saw exactly that signature coming from the direction of 3I Atlas. This was the first radio detection of any interstellar object in history. Previous attempts to observe 1I Oumuamua and 2I Borisov in radio wavelengths had come up empty. 3I Atlas, with its vigorous outgassing and high volatile content, finally provided enough molecular material for radio astronomers to detect. The hydroxyl absorption confirmed that the comet was actively releasing water ice that was being broken apart by solar ultraviolet radiation. The detection was historic, but also completely natural, exactly what you would expect from an icy comet heated by our sun. Let me explain the physics here, because it reveals something important about how comets interact with sunlight. When water ice sublimates from a comet's nucleus, water molecules stream outward into the vacuum of space. Solar ultraviolet light then photodissociates those water molecules, splitting them into their component atoms and radicals. One common product of this process is the hydroxyl radical OH, a highly reactive fragment that survives only briefly before participating in further reactions or drifting away into the solar wind. During its short lifetime, hydroxyl can absorb and emit radio waves at specific frequencies determined by quantum mechanical transitions within the molecule. The 1665 and 1667 MHz lines are particularly strong and have been used to study dozens of comets in our own solar system. Detecting these lines in 3I Atlas demonstrated that the same water chemistry operating in local comets also operates in interstellar visitors. The basic photodissociation process is universal. The Meerkat team, led by DJ Pisano of the University of Cape Town and Oleg Smirnov of Rhodes University, had attempted to detect 3I Atlas twice before in late September without success. At that time, the comet was farther from the Sun and less active. By October 24th, solar heating had intensified dramatically, driving water sublimation rates high enough to produce detectable hydroxyl abundances. The third attempt succeeded where earlier ones had failed because the comet had entered a more vigorous phase of activity. The timing of the detection coincided with solar conjunction, when 3I Atlas was positioned very close to the Sun as seen from Earth. This might seem counterintuitive. Would not the Sun interfere with the radio observations of a nearby object? In this case, the geometry actually helped. The comet's velocity relative to Earth created a Doppler shift that moved the hydroxyl absorption lines away from frequencies where solar or terrestrial interference would be problematic. The signals stood out cleanly against the background. For those tracking the alien hypothesis that has surrounded 3I Atlas since discovery, the radio detection might have seemed like a smoking gun moment. Radio signals from space have long been associated with the search for extraterrestrial intelligence. When the famous WOW signal was detected in 1977, it came as a strong narrowband radio burst that some speculated could be artificial. 3I Atlas, intriguingly, arrived from a direction that coincided within 9 degrees of the WOW signal's apparent origin. Could the Meerkat detection be evidence of something intelligent? The answer is definitively no. The hydroxyl absorption signature is unmistakably natural. The frequencies involved correspond exactly to known molecular transitions. The line widths match theoretical predictions for thermal broadening at the temperatures expected near the comet. The signal appeared precisely when and how it should if 3I Atlas were an icy body releasing water vapor under solar heating. There is nothing artificial about it. In fact, the detection removes one of the objections that skeptics had raised about the comet. Some had noted that 3I Atlas showed relatively little water emission compared to carbon dioxide, suggesting perhaps that it was not a typical icy body. The hydroxyl detection proves that water is indeed present and being actively released. The comet is genuinely icy, genuinely cometary, genuinely natural. The radio signature is the signature of ancient water ice from another star system finally sublimating in the warmth of our Sun. But the detection also revealed something surprising about the water loss rate. Even at a distance of 1.38 astronomical units from the Sun, where the comet's surface temperature would be lower than Earth's by roughly 15%, 3I Atlas was shedding water molecules at a substantial rate. This is unusual behaviour. Most comets from our solar system show relatively modest water activity at that distance, with sublimation rates increasing steeply only as they come much closer to the Sun. The elevated water loss suggests that 3I Atlas may have a lower thermal inertia than typical comets, meaning heat penetrates its surface more easily. Alternatively, the comet might have pockets of especially pure water ice that sublimate readily even at moderate temperatures. Or the carbon dioxide outgassing that dominates its activity might be entraining water ice particles in its flow, carrying them away from the nucleus before they would otherwise sublimate. Multiple mechanisms could explain the observation, and distinguishing between them requires additional data. Researchers are also interested in what the hydroxyl detection can tell us about the original composition of the comet. The isotopic ratios in water molecules, specifically the ratio of hydrogen to deuterium, carry information about the temperature and conditions where the ice formed. In solar system comets, deuterium to hydrogen ratios vary depending on whether the comet formed in the inner or outer regions of the protoplanetary disk. Measuring this ratio in 3I Atlas could reveal something about the environment around its parent star. Unfortunately, the Meerkat detection was not sensitive enough to determine isotopic ratios. The absorption lines provided presence information, but not the detailed spectroscopic precision needed for isotopic analysis. Future observations with other radio facilities might achieve better results, especially if the comet remains active as it recedes from the Sun over the coming months. The November observations also included a search for something very different. On November 5th, Meerkat conducted a search for narrowband radio transmissions from 3I Atlas, using a system designed to detect artificial signals. The BLUES backend, developed for the Breakthrough Listen initiative, analysed data across frequencies from 900 to 1670 MHz, looking for the kind of coherent engineered signals that technology would produce. The result was negative but still informative. Over 23,000 potential signals were detected during the observation, but every single one could be attributed to human-made radio frequency interference. None matched the position of 3I Atlas in a way that would indicate the comet itself was transmitting. The search established an upper limit on any potential technological transmission of approximately 0.17 watts over the observed frequency range. That is roughly equivalent to the power output of a mobile phone handset at the comet's distance. If 3I Atlas were broadcasting, it was doing so at a power level below our detection threshold. Avi Loeb noted this result with interest. The absence of a clear technological signal did not disprove his hypothesis about potential artificial origins, but it constrained the possibilities. If 3I Atlas were a technological object, it was not actively transmitting in radio frequencies we can detect. Loeb suggested that the Juno spacecraft, which will be near Jupiter when 3I Atlas passes through that planet's neighbourhood in March 2026, should search for lower frequency emissions that Meerkat could not observe. The radio story of 3I Atlas thus has two threads. The natural thread, represented by hydroxyl absorption, confirms that this is an icy comet, undergoing normal photodissociation chemistry as it interacts with sunlight. The technological thread, represented by the negative BLUES surge, rules out obvious artificial signals while leaving the door open for more exotic possibilities. Both threads contribute to our understanding of what this object is and what it is not. There is one more radio observation worth mentioning. In late November and early December, additional reports circulated about unusual radio characteristics associated with 3I Atlas. Some claimed that signals had been detected at specific frequencies, with patterns that did not match known natural phenomena. The timing and frequency drift of these emissions, it was said, were consistent with a moving object but did not match standard expectations for cometary radio behaviour. These claims remain controversial and unverified. The original reports came from sources that have not been corroborated by major radio observatories. Instrumental effects, terrestrial interference, and data processing artifacts can all create spurious signals that appear mysterious until properly analysed. The scientific community is waiting for peer-reviewed publication of any anomalous detections before drawing conclusions. What we can say with confidence is that 3I Atlas has made radio astronomy history by being the first interstellar object detected in radio wavelengths. The hydroxyl signature proves water activity, the isotopic potential awaits future measurement, and the technological search came up empty. These facts ground the discussion in evidence while speculation continues to swirl around the edges, and speculation has certainly intensified as we approach the December 19th flyby. Because beyond the chemistry and the radio emissions and the visual anomalies, there is a trajectory question that refuses to go away. Harvard astrophysicist Avi Loeb has identified what he calls an extraordinary coincidence in the path 3I Atlas is taking through our solar system. Its closest approach to Jupiter in March 2026 falls almost exactly at the boundary of that giant planet's gravitational sphere of influence. The odds of that happening by chance, Loeb calculates, are roughly 1 in 26,000. Is it coincidence, or is it precision? The Jupiter coincidence. On March 16th, 2026, 3I Atlas will pass within 53.6 million kilometers of Jupiter. That number might seem arbitrary, one distance among the infinite possibilities of orbital mechanics, but it is not arbitrary at all. It is within a margin of error so small it almost defies calculation, identical to Jupiter's Hill radius, and that coincidence has made Avi Loeb very uncomfortable. Let me explain what the Hill radius means, because it is crucial to understanding why this trajectory feature has attracted attention. Every massive body in space exerts gravitational influence on its surroundings, but that influence is not unlimited. At some distance, the gravitational pull of another body, typically the Sun in our solar system, becomes dominant. The Hill radius marks the boundary where a planet's gravity is strong enough to capture and retain objects as moons or satellites. Within Jupiter's Hill radius, the giant planet is the primary gravitational influence. Beyond it, the Sun takes over. For Jupiter, the Hill radius is approximately 53.5 million kilometers. The predicted closest approach of 3I Atlas to Jupiter is 53.6 million kilometers, with an uncertainty of plus or minus 60,000 kilometers. The difference between these numbers is about 100,000 kilometers, less than 1% of the total distance. On cosmic scales, where objects routinely miss each other by millions or billions of kilometers, this is remarkably precise alignment. Loeb has framed this as follows. If you were designing a trajectory to deliver an object to Jupiter's gravitational boundary, to the exact edge of the zone where Jupiter could capture satellites, you could hardly do better than the path 3I Atlas is following. The coincidence has a likelihood of approximately 1 in 26,000 if we assume the trajectory is random. That is not impossible by any means. Unlikely events happen all the time in a universe as vast as ours. But it is unusual enough to warrant attention. This significance becomes clearer when you consider what an object might do at Jupiter's Hill sphere boundary. This is the optimal location for performing what aerospace engineers call an Oberth maneuver. Named after the space travel pioneer Hermann Oberth, this technique exploits the relationship between velocity and gravitational potential to maximize the efficiency of propulsive burns. An object passing close to a massive body can fire its engines at the point of closest approach when its velocity is highest, and gain more change in orbit for the same amount of fuel than it would farther away. If 3I Atlas were a technological vehicle rather than a natural comet, approaching Jupiter's Hill radius would be strategically sensible. A mothership, to use Loeb's terminology, could use this position to deploy smaller probes into bound orbits around Jupiter with minimal energy expenditure. The deployed objects would remain within Jupiter's gravitational influence, potentially settling into stable positions at the planet's Lagrange points, where orbital maintenance requires almost no fuel. From there, they could observe the Jupiter system for as long as their systems remained functional. This scenario is pure speculation. There is no direct evidence that 3I Atlas is anything other than a natural comet. Every observation to date, from chemical composition to cometary activity to radio emissions, is consistent with an icy body of interstellar origin, doing exactly what icy bodies do when heated by a star. The coincidence of the Jupiter approach is striking, but coincidences happen. Drawing extraordinary conclusions from trajectory alone is not good science. And yet, Loeb has compiled a list of anomalies associated with 3I Atlas that he argues should not be dismissed. The trajectory alignment with the ecliptic plane of our solar system has a probability of about 0.2% if the object arrived from a random direction in interstellar space. The arrival from a direction coincident with the WOW signal has a probability of about 0.6%. The timing that brought the comet close to Mars, Venus and Jupiter, while being unobservable from Earth at perihelion, has a probability of about 0.005%. Each anomaly individually might be unremarkable. Combined, Loeb calculates, they represent a likelihood of less than 1 in 100 million, if 3I Atlas is a random natural object. This statistical argument is controversial among astronomers. The probability calculations depend on assumptions about what constitutes the appropriate comparison sample. If you select anomalies after the fact, specifically choosing features that seem unusual, you can make any object appear improbable. The universe contains countless objects, and some of them will inevitably display unusual features by chance. The real question is whether the anomalies are unusual compared to what we would expect from interstellar comets generally, and we have a sample size of exactly 3 such objects. Drawing statistical conclusions from 3 data points is hazardous. Loeb acknowledges these objections, but argues that the stakes are too high to ignore the possibilities. If 3I Atlas were technological, he says, the implications for humanity would be enormous. We would need to revise our understanding of our place in the universe, develop protocols for responding to extraterrestrial technology, and potentially prepare for scenarios ranging from benign observation to active intervention. The cost of being wrong about a natural comet is minimal. The cost of being wrong about alien technology could be catastrophic. This is the Pascal's wager of extraterrestrial intelligence. Even if the probability is low, the consequences if the hypothesis is correct are so significant that investigation is warranted. Loeb has called for intensified observation of 3I Atlas as it continues its journey, including searches for low-frequency radio emissions, monitoring for unexpected trajectory changes, and detailed imaging of any structures around the nucleus. He has suggested that the Juno spacecraft currently orbiting Jupiter should search for signals from the comet as it approaches in March. The scientific community has responded with a mixture of dismissal and qualified openness. Many astronomers consider Loeb's speculation unproductive, distracting attention from the genuinely fascinating natural science that 3I Atlas presents. Chris Lintott of Oxford University called the alien hypothesis absolute nonsense and an insult to the exciting work being done to understand the object. NASA officials have been diplomatic but firm, emphasizing that all data point to a natural comet and that there is no evidence of artificial origin. Others take a more nuanced position. The search for extraterrestrial intelligence is a legitimate scientific endeavour, and interstellar objects do represent a category where artificial probes could theoretically appear. Dismissing the possibility out of hand is not scientific either. The appropriate response is to conduct observations, gather data, and evaluate hypotheses against evidence. If 3I Atlas continues to behave like a comet as it recedes from the Sun, the alien hypothesis loses plausibility. If it does something genuinely unexpected, the hypothesis would warrant revisiting. What might count as genuinely unexpected? A sudden trajectory change that cannot be explained by outgassing or gravitational perturbations would be significant. Detection of a coherent radio signal with clear artificial characteristics would be significant. Observation of objects being released from the main body would be significant. Structural features visible in high-resolution imaging that defied natural explanation would be significant. So far, none of these things has occurred. 3. I-Atlas looks, acts, and smells like a comet. But the Jupiter approach will provide a crucial test. If Loeb is correct and the comet intends to perform some kind of maneuver at the Hill radius boundary, we should see evidence of that intention in the weeks leading up to March 2026. Trajectory refinements based on ongoing astrometric observations will either confirm the precise alignment or reveal that measurement uncertainties had made the coincidence appear more striking than it actually is. The Juno spacecraft will be watching. Ground-based observatories will be watching. If anything unusual happens, we will know. The broader context here matters too. Humanity has launched technological objects into interstellar trajectories. The Voyager spacecraft are even now drifting toward other star systems, carrying gold records with messages from Earth. In billions of years, those probes will pass through alien solar systems, and any intelligent observers there would face the same question we face with 3I Atlas. Is this natural or artificial? The fact that we have sent technology into interstellar space proves that the concept is not absurd. If we can do it, others might have done it before us. The hypothesis that interstellar visitors could include technological artifacts is not inherently unscientific. It is an empirical question that can be investigated through observation. What isn't scientific is assuming the answer before the evidence is in, whether that assumption is that 3I Atlas must be artificial or that it must be natural. The truth is that we do not yet know with certainty. We have strong evidence pointing toward natural origins and suggestive anomalies that invite further investigation. The responsible approach is to continue gathering data while remaining open to whatever that data reveals. As December 19th approaches and the comet reaches its closest point to Earth, observers will have their best opportunity to study 3I Atlas in detail. High-resolution spectroscopy may reveal new molecular species. Imaging may show structural features in the coma and jets. Astrometry will refine the trajectory prediction for the Jupiter encounter. Each observation adds information, and information is what ultimately distinguishes knowledge from speculation. The jets themselves deserve special attention in this context, because Loeb has pointed to another unusual feature of 3I Atlas that he believes supports the technological hypothesis. The collimated jets extending from the nucleus are not simply pointing away from the Sun as expected. Some appear oriented perpendicular to the solar direction, and at least one has been observed extending ahead of the comet rather than behind it. If these features are real and not observational artifacts, they would be difficult to explain with standard comet physics. They might indicate, Loeb suggests, directional control or deliberate maneuvering, or they might indicate that we simply do not understand all the ways that natural cryovolcanic activity can manifest. The next chapter examines what we actually know about these heartbeat-pulsing jets and what they might mean. Heartbeat pulses and collimated jets. In the days following 3I Atlas's emergence from behind the Sun, observers documented jet structures that stretched for millions of kilometers into space. These were not gentle plumes diffusing softly from the nucleus. These were focused beams of material maintaining coherence far longer than expected, as if guided by invisible channels or propelled by forces beyond simple sublimation. And some of them were pointing in directions that made no immediate sense. The standard model of cometary jets is straightforward. When solar radiation heats a comet's surface, it warms ice deposits that eventually reach sublimation temperature. Gas erupts from these active regions, carrying dust along in the flow. Because the Sun is the heat source, active regions tend to be on the sunlit side of the nucleus. The ejected material expands outward, pushed by radiation pressure and swept by the solar wind, creating jets that point generally away from the Sun or curve in that direction as they dissipate. 3I Atlas has displayed jets that defy this simple picture. Multiple observers have photographed plume structures extending perpendicular to the Sun direction, maintaining collimation across enormous distances. At least one jet has been documented pointing sunward, ahead of the comet's motion rather than trailing behind. These anti-tail features, as they are sometimes called, are not unknown in cometary science, but they are uncommon, and their appearance in 3I Atlas has generated considerable discussion. Avi Loeb has seized on these features as potential evidence of technological control. In his view, jets that maintain tight collimation for millions of kilometers and orient in unexpected directions could indicate propulsive exhaust from an engineered object, rather than passive outgassing from a natural body. He has described images showing plumes extended perpendicular to the solar direction and ahead of the object, suggesting this could be a technological signature of illuminating or clearing the path from hazardous micrometeorites. The hypothesis is that 3I Atlas might be using directed jets for navigation or protection as it traverses our solar system. The scientific community offers alternative explanations. Comet nuclei are not uniform spheres but irregular lumpy bodies with complex surface geography. Active regions can be located anywhere on the surface, not just the subsolar point. As the nucleus rotates, jets from these regions sweep through space in patterns determined by the spin axis and rotation period. A jet that appears perpendicular to the Sun direction at one moment might be perfectly aligned with expectations when the rotation phase is properly accounted for. The apparent sunward orientation of some features could also have geometric explanations. When a comet's tail happens to lie nearly in our line of sight, projection effects can create illusions. Material actually moving away from the Sun can appear to be moving toward it if the viewing angle is unfavourable. This is similar to how a road sign viewed from an angle can appear to point in a different direction than it actually does. Careful analysis of multiple observations from different times and angles is needed to determine the true three-dimensional geometry. Furthermore, cometary jets are not simple streams of material moving in straight lines. The gas and dust interact with each other and with solar radiation in complex ways. Electromagnetic forces affect ionized gas. Radiation pressure decelerates dust grains differently depending on their size. The solar wind shapes the outer coma. What appears as a collimated jet in one wavelength might look diffuse in another. Interpreting jet images requires sophisticated modelling that accounts for all these factors. The heartbeat pattern that some observers have noted adds another layer of complexity. Images taken over time show jets that appear to brighten and dim in repeating cycles. This pulsation could simply reflect the rotation of the nucleus, with active regions cycling in and out of sunlight. A vent on the equator of a comet with a 6-hour rotation period would face the sun twice per rotation, producing activity peaks every 3 hours. The heartbeat would be the comet's own rotation clock ticking away in the rhythm of its jets. But Loeb has described this periodic brightening as potentially something more. If the pulsations did not match a simple rotation model, if they occurred at intervals that could not be explained by geometry alone, that would warrant closer examination. He has not claimed definitive evidence of artificial pulsation control, but he has raised the possibility as something worth investigating. Determining whether the jet patterns are natural requires detailed observations and modelling. Astronomers need to measure the rotation period of the nucleus through light curve analysis. They need to map the locations of active regions through high-resolution imaging. They need to model the expected jet orientations based on spin axis, rotation phase, and active region distribution. Only when the predicted behaviour can be compared against observed behaviour will we know whether anything truly anomalous is occurring. The data gathered so far is consistent with natural explanations. The spiral jet patterns photographed by the Spanish team fit models of material ejected from a rotating source. The bright coma documented by JUICE shows the kind of activity expected from an icy body near perihelion. The dust and ion tails visible in multiple images demonstrate normal interaction between cometary outflow and the solar environment. Nothing yet observed requires invoking artificial processes. This does not mean the jets are uninteresting from a natural science perspective. Quite the opposite. 3i Atlas provides an opportunity to study how interstellar comets behave differently from local ones. The carbon dioxide-dominated composition might create jets with different expansion velocities than water-dominated jets in solar system comets. The ancient irradiated crust might produce distinctive patterns as cryovolcanic eruptions punch through at different locations. The potentially patchy internal structure might generate multiple jets from different source regions with varying compositions. Comparing these features to what we know from solar system comets will teach us about the diversity of icy bodies across the galaxy. Are all interstellar comets carbon dioxide rich, or is 3i Atlas unusual? Do they all show vigorous activity at large distances from the Sun, or is that specific to this object's composition? Are the jet patterns typical of comets formed in different stellar environments, or are they unique to wherever 3i Atlas originated? Each question connects to broader issues of planetary formation and interstellar material transport. The jets also provide a window into the comet's interior. Because different volatiles sublimate at different temperatures, the jet composition changes as solar heating penetrates deeper into the nucleus. Early in the approach, carbon dioxide with its low sublimation point dominates. As the comet warms, water ice begins contributing more significantly. By monitoring how jet composition evolves with distance from the Sun, researchers can infer the layered structure of the nucleus and the distribution of different ice species within it. This vertical profiling is especially valuable for an interstellar object. 3i Atlas formed in a protoplanetary disk with unknown temperature gradients and composition patterns. The layering of its nucleus preserves a record of those ancient conditions. Water ice condensing at one distance from the parent star, carbon dioxide condensing at another, other volatiles condensing at yet other locations. All of that layering survives frozen in the nucleus until solar heating unlocks it through jet activity. We are watching a geological core sample from another star system being extruded into space before our eyes. The collimation of the jets is itself informative. When gas escapes from a vent on a comet's surface, it initially expands freely into the vacuum, but if the vent is narrow or the subsurface cavity has a particular shape, the escaping gas can be focused into a jet that maintains coherence over significant distances. The more focused the jet, the more constrained the source geometry must be. Observing tightly collimated jets in 3I Atlas tells us something about the morphology of its active regions, information that would be impossible to obtain through direct imaging at interstellar distances. Some researchers have proposed that the unusual jet features of 3I Atlas result from its unique composition interacting with its unique thermal history. An object that spent billions of years in deep freeze develops an irradiated crust with properties unlike the pristine interior. When solar heating creates pressure differentials across this crust, the resulting eruptions might be more violent and more focused than typical cometary activity. The crust acts as a pressure cooker lid, containing expanding gas until the pressure exceeds some threshold, then releasing it suddenly through whatever weakness gives way. This explosive release model could explain both the vigor of the jets and their directional characteristics. Rather than steady seeping from porous surfaces, we would be seeing intermittent blasts from localized pressure relief valves. The orientations would depend on where the crust happened to be weakest, which might not correlate with the subsolar point at all. The periodicity would depend on how long it takes pressure to rebuild after each release, which might or might not align with rotational cycles. Testing this model requires observations that can resolve the jet structure over time, tracking individual features as they form, expand, and dissipate. The December closest approach offers the best opportunity for such monitoring. High-resolution imaging from Hubble and ground-based adaptive optic systems may be able to catch jets in the act of forming, providing constraints on the eruption mechanism that no previous interstellar object has yielded. Regardless of whether the jets turn out to be natural or anomalous, they are contributing to the ongoing transformation of 3I Atlas. Every kilogram of material ejected into space is mass the comet loses forever. The nucleus is eroding as we watch, shrinking particle by particle and molecule by molecule. By the time 3I Atlas exits our solar system, it will be measurably smaller than when it arrived. The brilliant activity that makes it so visible now is also the process by which it destroys itself. This erosion raises a question about the comet's future. After leaving the solar system, 3I Atlas will coast outward through interstellar space for eons, slowly cooling as the sun's influence fades. Will it retain enough volatile material to be active again if it passes close to another star, millions or billions of years hence? Or has this solar encounter depleted reservoirs that can never be replenished? We cannot know the answer, but we can document the extent of the loss while observation remains possible. And observation will remain possible for several more months as 3I Atlas recedes into the outer solar system. But there is a deadline approaching, both in calendar time and in the comet's fading brightness. The December 19th closest approach marks a turning point. After that date, every kilometre of increasing distance means fainter signals, harder observations, and diminishing scientific returns. What happens after December 19th will determine how the story of 3I Atlas enters the historical record. What happens after December 19th in 8 days, 3I Atlas will reach its closest point to Earth. 170 million miles will separate us from the most studied interstellar object in history. Then the distance will begin to grow. Every day after December 19th, the gap widens. Every week, the comet dims. Every month, our observations become more challenging. The window that opened in July when the Atlas telescope first spotted this visitor will gradually close, and eventually 3I Atlas will fade beyond even our most powerful instruments, disappearing into the darkness between stars as if it had never been here at all. But the science does not end on December 19th. It shifts into a new phase, one focused on maximizing what we can learn during the extended fade-out and preparing for the milestone event that awaits in March 2026. The James Webb Space Telescope has observations scheduled for December that will track how the comet's carbon dioxide-dominated coma evolves as it moves away from the Sun. At perihelion, solar heating drove carbon dioxide sublimation at ferocious rates. Now, with distance increasing and temperature dropping, that activity should decline according to predictable physical laws. Webb will measure the actual decline and compare it to models, testing whether 3I Atlas behaves as expected or continues to surprise us. ALMA and other radio observatories will continue monitoring methanol and hydrogen cyanide production as the comet recedes. The power law relationships established from pre-perihelion observations predict how these molecules should decrease with increasing heliocentric distance. Confirming those predictions validates our understanding of the comet's volatile inventory. Deviating from those predictions would indicate that something about the interior structure or composition differs from our assumptions. Ground-based telescopes will track the comet's light curve, watching brightness fade night by night. They will monitor the coma morphology, documenting how jet structures weaken and disappear as the activity driving them diminishes. They will measure colours and spectra, searching for changes that reveal evolving chemistry as different volatile species freeze out at different temperatures. Each data point adds to a timeline of cometary behaviour that spans from discovery through departure. By January 2026, 3I Atlas will have crossed 2 astronomical units from the Sun, roughly the distance of the asteroid belt. Activity should be noticeably reduced from the perihelion peak. By February, the full JUICE dataset will finally arrive, providing close-range observations from November that complement the more distant measurements. Researchers will spend months analysing that data, comparing it to what Hubble and Webb and ground-based facilities gathered, building a comprehensive picture of the comet's behaviour through its most active phase. And then comes March 16th, 2026, Jupiter. The predicted closest approach to the giant planet will occur at a distance of 53.6 million kilometres, essentially grazing the boundary of Jupiter's gravitational sphere of influence. From Earth, 3I Atlas will be faint but still observable, positioned against the star field where careful astrometry can track its trajectory with high precision. If the comet deviates from predicted paths due to gravitational interactions, unknown outgassing, or any other cause, we will measure that deviation. Avi Loeb has urged that the Juno spacecraft be prepared to observe 3I Atlas during this encounter. Juno, currently in orbit around Jupiter, studying the giant planet's atmosphere and magnetic field, could search for radio emissions from the comet using its dipole antenna. The frequency range from 50 Hz to 40 MHz is inaccessible to Earth-based telescopes, but open to Juno's instruments. If 3I Atlas were transmitting at low frequencies, Juno might be positioned to detect signals that would otherwise go unheard. Whether NASA will modify Juno's observation schedule for this purpose remains uncertain. The spacecraft has primary science objectives, and diverting attention to a speculative search for alien signals is not trivially justified. But the opportunity is unique. No other probe will be in position to observe 3I Atlas at Jupiter range. If the observation is not made, it cannot be repeated. After Jupiter, 3I Atlas will accelerate outward, leaving the realm of the planets behind. By late 2026, it will cross Neptune's orbit. By the end of the decade, it will be beyond the Kuiper Belt, still travelling at 130,000 miles per hour, still carrying whatever secrets it has not yet revealed. Eventually, within years or decades, it will fade beyond detectability entirely. Our brief encounter will have ended, but what we learned will endure. The data archived from 6 months of intensive observation will be analysed for years, probably decades to come. Graduate students not yet born will write dissertations on aspects of 3I Atlas that current researchers do not have time to explore. The comet will become a benchmark for comparison when the next interstellar visitor arrives, as one inevitably will. Each new detection builds on the previous ones, and 3I Atlas has given us more to build on than either Oumuamua or Borisov. The legacy matters because interstellar objects are not rare cosmic accidents. They are a population. Models predict that the solar system should contain thousands of interstellar interlopers at any given time, most too small or too distant to detect with current technology. The fact that we have found 3 in 8 years suggests that the population is at least as numerous as predicted, perhaps more so. As survey telescopes become more sensitive and sky coverage becomes more complete, we'll find more of these visitors. Each one will offer a sample from a different star system, a chemical postcard from an alien origin. 3I Atlas is special because it is the first interstellar visitor large enough and active enough and close enough to study in real detail. Oumuamua was small and inactive and discovered only as it was leaving. Borisov was more comet-like but smaller and more distant. 3i Atlas hit the jackpot of observational circumstances, arriving on a trajectory that brought it through the inner solar system, displaying vigorous activity that made its composition measurable and remaining accessible to our best instruments for months. We may not get this lucky again for years or decades. The next interstellar comet might be fainter, faster, or more poorly positioned. It might arrive during a period when key space telescopes are offline or otherwise occupied. It might display little activity, keeping its chemical secrets frozen inside an unrevealing nucleus. 3i Atlas represents an opportunity that we recognized and seized. The scientific community mobilized resources, coordinated observations, and prioritized a visitor that will never return. That response is something to be proud of. As I record these words, the comet continues its outward journey. The X-ray halo that first appeared in XRISM data is likely still glowing, though perhaps fainter now as activity subsides. The twin tails visible in the JUICE image are still streaming behind the nucleus, though shorter and less distinct as the material supply diminishes. The green glow that puzzled observers in September may still be present, though competing with the fading coma for visibility. The methanol and hydrogen cyanide are still venting into space, though at declining rates that will eventually approach zero. Somewhere in that shrinking envelope of gas and ancient ice is a frozen record of another star's protoplanetary disk, a sample of chemistry from 7 billion years ago, a messenger carrying information that our instruments are straining to decode. We have read part of the message: carbon dioxide and water, methanol and hydrogen cyanide, nickel and cyanogen, X-rays and radio waves, twin tails and spiral jets, green fluorescence without an obvious source. The pieces assemble into a portrait of an object unlike anything we have studied before, an object that formed elsewhere and travelled here and will leave again, never knowing and never caring that a small blue planet briefly turned its telescopes toward the sky and asked what it was. That asking is what makes us human. The curiosity that drives us to study a distant comet is the same curiosity that built every observatory and launched every spacecraft and trained every astronomer who has contributed to this effort. We look up because we cannot help looking up. We ask questions because questions are how we understand our place in the universe, and when something as extraordinary as 3i Atlas passes through our neighbourhood, we drop what we're doing and we watch, because we may never see anything like it again. Thank you for staying with me through this journey. Thank you for your curiosity and your patience and your willingness to follow the science wherever it leads. If you have enjoyed this exploration of 3i Atlas and what it means for our understanding of the cosmos, please take a moment to like this video and subscribe to the channel. Your support helps us continue bringing you these deep dives into the mysteries of space and time. As always, the information presented here reflects the best available data and scientific consensus as of the recording date. New observations may reveal additional details or require revisions to current understanding. Science is a process of continuous refinement, and what we know today is built on what we learned yesterday and will be improved by what we discover tomorrow. Now the hour grows late and the stars are calling. Somewhere out there, 3i Atlas continues its eternal journey, carrying its cargo of frozen chemistry toward destinations we cannot imagine. Sleep well, dream of distant suns and ancient comets, and know that the universe is full of wonders waiting to be discovered. Until next time, this has been your guide through the cosmos. Good night.